All right, I'm going to do a video covering some of the problems from the 3-4 outline. Um, Several of them we stopped before we completely simplified them. And then I'm also going to do a question from homework that I started but didn't finish as well. Okay, so I wanted to start with question number 26 from the 3-4 outline. All right, so this one was going to involve, let me blow that up a little bit. Okay, so this one was going to be a product rule problem because we have a function of x and it's being multiplied by a different function of x. All right, now this 16 minus x squared is under the radical. So before you start doing the derivative, it pays to rewrite that using exponents so that you can apply the power rule. Okay. All right, so think about this being where the multiplication is, so that we're going to wind up doing the product rule now. So what we're going to do is we're going to do the derivative of the first function, which would be 2x, multiplied by the second function as is. Okay, then we're going to add to that the first function as is, and then we're going to do the derivative of the second function. And this is where sometimes people mess up because it's got the inside function here. This is more than just x. It's a function of x. So let me do this part in red. Okay, so I'm getting ready to do the derivative of that second function. So I'd have to bring the 1/2 down. Then I would take the 16 minus x squared to the negative 1/2. And usually y'all remember that. But don't forget to look at that inside function and be sure to take the derivative of it, which would be negative 2x, and include that. Okay. All right, so that's it. Now, from here to the bottom, I'm going to be simplifying stuff. So what I like to do first is I like to get the two terms written in a comparable way so I can then do that factoring step. So this is times all in here. So I'm looking at this, this, and this, and I'm going to multiply it all together. So 1/2 times 2 would be gone, but I do have a minus, and then x squared times x would be x to the third with that 16 minus x squared to the negative 1/2 power. All right, now once I get to there, I've kind of got it organized. And so at this point, I can see that I could pull out that 16 minus x squared. I have the same base here, so I'm going to factor that out. Okay, I'm going to factor it out and move it way over here. And then I just happen to notice there's also an x, so maybe I'll go ahead and factor that out as well. So I'm going to bring out an x, and then the 16 minus x squared. Let me move it over even a little bit more because it kind of helps sometimes when the part you factored out is over here to the left. Use the smaller exponent, and then I'm going to see what's left. Okay, so I'm looking at, well, what do I need? What do I need right here to make that first term? So I'd need the 2, the x I'm getting from here, and then I'd need 16 minus x squared to some power. And the power I would need, the exponent I would need, would have to be something so that when I added it to the negative 1/2, I get positive 1/2. So it's to the first power. Okay, then in the second spot, I would have minus x squared, and then really just times 1 because I've already factored out all of that. Okay, so I see an x. I see a 16 minus x squared to the negative 1/2. Inside here, I could distribute. So I'd get 32 because that's just to the first power. So that's really just 16 minus x squared. So I'd get 32 minus 2x squared minus another x squared. Okay. So these are like terms I can put together. So I wind up with an x. That's 16 minus x squared to the negative 1/2, and then 32 minus 3x squareds. Okay, I'm going to go up here with it. Well, actually, I'm going to use that later. Let me go down here with it. Okay, so I'm going to wind up with, I can see the x that I would wind up having on top there. Okay, along with the 32 minus 3x squared. Okay. And then down here, I would move that 16 minus x squared, put it under the radical. And there you have it. Okay. All right, so take a moment, pause the video if you need to make sure that part makes sense. And then we're going to do 28, which is another messy algebra problem, basically. Has a quotient rule in it, though. Okay. All right, so let's take a look at 28. Before we get started, we could turn it into a product rule, but that normally doesn't make it that much easier because of the negative exponent. So I'm going to leave it as a quotient rule question, but I am going to take it in the denominator and rewrite it using 1/2 power. Okay. So then I'm going to get ready to do y prime, and I'm going to use the quotient rule. So I know the derivative of the numerator is 1. Let's do those derivatives in red right here. So the derivative of the numerator is 1. And notice the derivative of the denominator would be 1/2 x to the 4th plus 4 to the negative 1/2. And then you'd have to multiply by the derivative of the inside, which is 4x to the 3rd. Okay, so the quotient rule isn't just derivative of top divided by the derivative of the bottom. Okay, you know that by now. You do the derivative of the top times the bottom function as is minus the top function as is times the derivative. I want it to be red. Okay, top function as is times the derivative of the bottom function, which is 1/2 x to the 4th plus 4 to the negative 1/2. Oh, I wish I had cleaned that up before we did that. Oh, well, I'll clean it up in the next. But I should have, since I took the time to do the derivative right here, I should have gone ahead and simplified that. See how that's 2x to the 3rd? Let me go ahead and just think that through as I write this. So the derivative of the bottom part we have right here, and I can put it together. The 1/2 times 4 would be 2x to the 3rd with the x to the 4th plus 4 to the negative 1/2 power. Okay. All right, and then remember the quotient rule also has, then all of that gets divided by x to the 4th plus 4 to the 1/2, all squared. Okay. So let's see, in the numerator, I just have really x to the 4th plus 4 to the positive 1/2 power. And then this is times. So let's put that together. So that would be minus 2x to the 4th, and then x to the 4th plus 4 to the negative 1/2 power. And then down here, I've got a power being raised to a power. So those exponents could be multiplied. And that would give me x to the 4 plus 4 just to the first power. Okay. All right. So we've got it cleaned up nicely. We're ready for that factoring step. So I'm going to factor out the x to the 4 plus 4 to the negative 1/2 power. And I'm going to see what's left on top. The first term, I would have an x to the 4th plus 4. And I would need it to be to the first power. So when I add a negative 1/2 and positive 1, I get a positive 1/2 right here. Then I would have minus 2x to the 4th but nothing else, because the x to the fourth plus 4 to the negative 1/2 power was all factored out in the front. So this x to the fourth plus 4 to the negative 1/2, and then notice this is to the first power inside here. So that's really an x to the fourth plus 4 minus 2x to the fourth. So 1x to the fourth minus 2x to the fourth would be negative x to the fourth plus 4. That's the same as 4 minus x to the fourth. Okay. All right, so really here, I would just rewrite it without a negative exponent, and I would change that negative, the fractional exponent, I would change that into a radical again. Okay, so I'm going to wind up having the negative x to the fourth plus 4. Oh, I dropped my denominator. I don't know if you noticed that. So that still has a denominator of x to the fourth plus 4. This still has the denominator x to the fourth plus 4. So I have negative x to the fourth plus 4 divided by, or times, divided by. Okay, hold on. I lost my bearings when I noticed I missed that denominator. So let me just backtrack for a second. So the factoring step was here, okay, where I factored out the lowest exponent. What was left was x to the fourth plus 4 to the first power, take away 2x to the fourth. So x to the fourth, take away 2x to the fourth, because this is to the first power, so I can really just think of it as x to the fourth plus 4 with no parentheses. So those are like terms, become negative x to the fourth, brought down the 4. Now the thing I squeezed in underneath there was this denominator. Okay, so I'm just carrying that along. All right, and now I was getting ready to fix this, rewrite this as good as it gets. So I have a negative x to the fourth plus 4, and then I'm going to bring the x to the fourth plus 4 down, make it a positive 1/2, and then I still have an x to the fourth plus 4 sitting there. Okay. All right, so you could think of this one as negative x to the fourth plus 4, square root of 4x plus 4, times the x to the fourth plus 4. Okay. Now you notice though that these were the same base. I like to consolidate that. That would wind up being x to the fourth plus 4 to the 3/2. Okay, so I'm really looking from here more than what you see next to it. And then I would think about that as negative x to the fourth plus 4 over square root of that cubed. Okay. All right. And these are both okay. Personally, I like it like that, so that if I'm asked to find what the slope is at a certain point, I think it's easier to calculate it when these are not separate. Okay. All right, so that one got a little bit messy there. I hope you were able to follow along when I went back and put that denominator back in there. I just don't want to start the whole video over again. Okay. All right, so I just wanted to do those two. Those are probably two with the messiest algebra in them. From there, then I wanted to look at, let's see, what was the other one I wanted to do? I had a couple circled that I wanted to do in particular because I felt like I either rushed them or didn't do them. Oh, let's look at 36 in this area. This one right here I skipped over. All right, so this one is secant of 6x. So if you put a number in for x, you would multiply by 6 first, then do the secant. So you start with secant when you do the derivative, and you think, okay, the derivative of secant is secant tangent. So it would be secant 6x times tangent 6x. And this really means this. It's the input. The 6x is the input to those functions. And then you'd have to multiply by the derivative of the inside, which would just be 6. All right, so that one turns out, that one just turns out to be 6 secant 6x tangent 6x. And you don't need the parentheses on the 6x necessarily. Okay. All right. Then I thought it would be good to jump to question 49 from homework. That was the one someone asked about, and I did most of it. So let me get a new blank document real quick. And we'll look at this as 49 from homework. Let's finish it. Okay, this is what it looked like. It was y equals sine. Then it had square root, and it had a cotangent, 3 pi x, and your job was to do the derivative. Okay, so if I put a number in for x, I'm going to multiply by 3 pi, do cotangent of that, take the square root, and then do sine. So there's like 4 functions that have been composed here. One thing I would do before I start the derivative is rewrite that radical part. And it's around all of the cotangent 3 pi x. That's being raised to the 1/2 power, okay? All right, then I would do the y prime, okay? All right, so the last thing done, the last function that you would run through is sine. So the derivative of sine is cosine. So you do cosine of all this raised to the 1/2 power. But then you got this chain going on. Now you're going to deal with the square root, or the raising to the 1/2 power. So you're going to multiply that by 1/2 cotangent 3 pi x, okay, raised to the negative 1/2. Okay, so you've dealt now with the radical. Now you're going to do the derivative of cotangent, okay, and that is, can't get it to write. There we go. And that is negative cosecant squared x, not x though, negative cosecant squared 3 pi x. Okay, just like the derivative of tangent is secant squared, your input. So your input to the cotangent function is 3 pi x. Derivative of cotangent would be negative cosecant squared, and it needs to stay your input. And then the last thing I'll do is I'll deal with the derivative of 3 pi x, and that would be 3 pi. All right, so that is it. Okay, so now let's see what I can do to make that look a little better. So this is all times here, 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 and here. But it's not times between cotangent and 3 pi x. That's a function, so it's not times there. So I'm going to take the negative and the 3 pi and the 1/2, and I'm going to think about that. That would be negative 3 pi over 2. Okay. Then for now, I'm going to think about this cotangent. Inside here, I have cotangent. I've got a parenthesis wrong somewhere, and I gotta get that fixed. Oh yeah, this has to end right here. Okay. All right, there we go. Okay, so when we did it, we did the derivative of the cosine first, and then that had all the cotangent 3 pi x raised to the 1/2. Then we multiply by the derivative of the cotangent 3 pi x raised to the 1/2. That's this piece here. Okay, so we continued. We did the derivative of the cotangent 3 pi x. That's the negative cosecant squared 3 pi x. And then we did derivative of the inside, got the 3 pi. Okay, so now we are cleaning it up. So we brought the 3 pi, the negative, and the 1/2 together. That would be negative 3 pi over 2. All right, then I'm going to have cosine. And let's go ahead and put this back under the radical. So that 1/2 power is really, that was okay the way I had it with there, is really on all of this, okay? So it's square root of cotangent 3 pi x, okay? Right? So that's that part. Okay, then here the cotangent 3 pi x, again, raised to a power, but it's to a negative 1/2 power. So that's going down here, and I'm taking the square root of that. And then I have cosecant squared, which should just be up here on top. And I'm just going to make clear that 3 pi x is the input. And that should be it. I would probably take this and put it in front so I don't get confused about what's under the radical. Of 3 pi x, and then cosine square root cotangent 3 pi x. And then don't be tempted. You see that cotangent 3 pi x under the radical? You want to try to cancel it, but you've got the cosine of it there. Cosine is not cosine times that, so you can't knock out the times that are left. Are kind of, nope's not there. The times that are left are here and here, but not between the cosine and that. All right, so that would be a good stopping point right there. Okay, that one we did most of the way, but I wasn't sure we got to that very end piece. All right, I'm going to go ahead and do more from 3-4, but I think I'll stop the video before I get to the additional problems. Let's see how many I got left. Oh no, I think I'll just continue. I just have a couple more I want to do. So let me go ahead. This might get longer than I like videos to be, but you can just speed through it. All right, so another one I circled is from the 3-4 handout. Wanted to look at question number, I had marked that we had not done number 92. So let's look at 92. Okay. So on that one, we start out with natural log, and we have secant x plus tangent x, absolute value of that. Okay. Whether there's absolute value there or not, when you do the derivative of a natural log, it's 1 over your input. So we'd get that. And then we have to multiply by the derivative of this input right here. Okay. And this is a plus. So we're not using a product rule. We're just doing the derivative of secant, and then we're doing the derivative of tangent. So the derivative of secant would be secant x tangent x. Okay. And then we'll add to that the derivative of tangent, which is secant squared x. Okay. All right. So what I'm winding up with on this one is I'm getting the secant x. All of this part is on top. Secant x tangent x plus secant squared x. All of that's over secant x plus tangent x. Okay. And so now I'm just going to see if I factor or see if there's any obvious, trig identities that I might be able to use to clean that up. Okay. So I'm noticing in the numerator, there's a secant x that's common to those two terms. So I'm going to factor that out from the first term, and I'd have tan x left. When I take secant out of the second term, I have one secant x left. And then notice that the secant x plus tangent x, that what order they're in doesn't matter because addition is commutative. So the secant x plus tangent x, that's going to cancel out, and you'll wind up with secant x at the end. So that's the final answer on that one. Okay. All right. All right, and then we did the second derivative on question number 126. I mean on 124, but not on 126. So I'm going to go do that. So let me go to question 126. I'm going to do the second derivative. Let me just get this one takes a while. So this is from the 3-4. Actually, I think I have the 3-4 still open. Let me go to doing the second derivative. They're near the end. Question 126. I'm probably going to need plenty of paper. This one is kind of tedious. See if you can follow through with me. So this one said second derivative, but we start by just doing the first derivative. I think it does help for you to see it carefully. So this is the same as secant of pi x, all getting raised to the second power. So you have x being multiplied by pi, then you're doing secant, then you're squaring. So when you get ready to do the derivative, you have to deal with the squaring function. So you bring down the 2, you keep it secant pi x, and then 2 minus 1 right here would be just 1. Then you got to multiply by the derivative of the inside and see the secant. So you're going to do the derivative of secant, which is secant your input times tangent of your input. And then you got to take the derivative of pi x, which is pi. Okay. So the first derivative portion of this is not too bad. Okay. And this is all times, so we can rewrite it with 2 pi. And then that would be secant pi x, and another secant pi x would be secant squared pi x. And then we have a tangent x still, tangent pi x still. Okay. Okay, so we have 2 pi, secant squared pi x, tangent pi x. But that's just the first derivative. Okay. Now I'm getting ready to do the second derivative. I'm going to move way over here because it's going to be kind of longer than you think. Could be longer than you think. Because see this times right here? I can do this as one function of x, and then here I've got another function of x. So I'm going to have to use the product rule. Okay. Okay. So let's get ready for the second derivative. So I'm going to do the derivative of this first function. So it would be 2 pi. Ooh, it's worse than you think. I'm going to write that squared. Make sure you see it as secant pi x squared. Okay. So I'm going to have my exponent is going to come down. It's going to, when I do the derivative. So it's going to be 2 times the 2 pi times the secant of pi x, now to the first power, times the derivative of secant, which is secant pi x tangent pi x, then times the derivative of pi x, which is pi. All right, all that I just did was just the derivative of the first function. So I need to multiply that. We'll change to a different color. Multiply that by the second function as is. But there's way more than that. It's much longer than that. I'm going to have to go to another line because I'm going to have to add to that the first function as is. So this is just a big plus, and then I'm coming down and writing the rest. So this is the first function as is times the derivative of the second function. The second function is tan pi x. So the derivative of tan pi x would just be secant squared pi x. And then derivative of the inside would be pi. Okay. Okay. All right. Now, I'm going to work on this a little bit. See what I see. So here's the plus that separates those two terms. So I'm going to work on this whole first term here, seeing if I can get it organized and collected in my mind better. And this is now just to the first power. This is times let's get all those time symbols in there. Okay, so what I'm seeing in that first part is 4, a pi here and a pi there, makes it 4 pi squared. Okay. Then I see a secant pi x and another secant pi x, and they're getting multiplied. So that's a secant pi x that's being squared. Okay. So I've taken care of these and this, and now these two, and then I still have a tangent pi x in there. That's, oh, and I've got 2 of them because I have that one and this one. So that's also squared. Okay, that's all that first term. All right, now let's see how the second one cleans up. So there I have a 2 pi and another pi, which would be 2 pi squared. Then I have a secant pi x that's squared and another, this is really secant pi x squared. So I have a secant pi x squared and another secant pi x squared. So I really have a secant pi x, and it's to the 4th power on that one. Okay. All right. Now at that point, I'm thinking I might do some factoring. So I'm going to pull out a 2 pi squared and the secant pi x squared. All right. And when I do, I'll have a 2 left from there. And then I'll have tangent pi x. And then plus a secant pi x still squared. Okay. All right, now what can be really hard on some of these, this right here, by the way, let me just double check. I like to check each step, and then I sometimes catch things I've left off. That still had a squared on it. Okay, so I factored out a secant pi x squared, so 2 tan pi x squared plus the secant pi x squared. Okay. All right, good so far. All right, then I'm thinking I've got a ton of secants in here, and then I have this tangent business. So I'm thinking I might be able to adjust it a little bit without using a super complicated identity, but I'm not really going to expect you to do a whole lot with your identities on the test, right? But I just wanted to go ahead and get you to think a little bit about how, the one that I expect you to know for sure, this cosine squared x plus sine squared x equals 1. I'm noticing down here I've got a tangent that's being squared and a secant that's being squared. I have tangents and secants. So what I'm going to do is see if I can create from the Pythagorean identity. I want to remember what the identity was that related tangent and secant. So if I divide sine by cosine squared x, sine squared x by cosine squared x, I'd get a tangent. So let me divide everywhere by cosine squared x. And that'll give me the other identity that's another Pythagorean identity. It's 1 plus tan squared x equals, and 1 over cosine is secant, so secant squared x. This is the identity that I'm going to use now, because what I'm going to do is take that and remember that tangent squared x is the same as secant squared x minus 1. So right here, I'm going to use that. I'm going to replace this part right here, the squared and everything, with secant squared. I'm in red, good. So I'm going to replace that with secant squared pi x minus 1. Okay, so you'll still have 2 times that plus the secant pi x here being squared, and this still in front. Okay, and that's now correct. Okay. And let's see, I need that Was that all multiplied? This has a big multiplication, so that needs to be like that. Okay, so I have so if I do that, so then that's 2 pi squared secant squared pi x. Then this would be 3, because that's to the first power. This would be 3 secant squared pi x. And then that 2 would get distributed. Okay. Ah. All right, I'm trying to decide how it would look best. So that's what I'd get if I factored out everything I could factor out. And you could stop there at that point. And I don't really think I would expect you to do this. Okay. All right, so I may revisit that one. I may look at it again and see if I can figure out another trick or something to clean it up a little bit. But I just wanted to get in there and work a little bit with the second derivatives. I can't give you one quite that messy when it comes time for the test. It would be, more than you could really handle in the time allowed. All right, one last one, and then we're done with all the little details from 3-4. Let's take a look at this one. On this one, just want the equation of the tangent line to the graph at a point. So that involves slope. So you're getting ready to do the derivative. This looks like a power function already, so you're ready to use the general power rule. You take 1 away from 2/3, and you'll get -1/3. Don't forget to do the derivative of the inside, which would be -2x. Take a moment maybe to clean that up a little bit. Maybe remember what that is. There's a 3 down there. Negative means it would move to the denominator. It was 1/3, so it'll be a cube root. Maybe rewrite it like that. Now you need y prime of 1. So you put 1 in for x, and you evaluate that. So you'll get a -4, and then here we'd have 3 times the cube root of 9 minus 1, which would be 8. So that's going to wind up being -4 over 3 times 2, right? So that'd be -4/6, which would be -2/3. Okay. So you've gotten the slope, and then you finally take the slope at that point together with the 0.14. And you do y minus 4 equals -2/3 x minus 1. Distribute. Okay. And then I like to go ahead and leave it in slope-intercept form. So I would add 4 to both sides and get y equals -2/3 x. And then let's see, that's 4/3 would be 4 would be 12/3. So that'd be plus 14/3. Now what you'll probably see them do, if you're looking in the back of the book, is they'd get rid of the denominator by multiplying by 3 everywhere. Then they'd bring the 2x over here by adding it to both sides, and they'd subtract 2. And they'd wind up with it looking like that. So it looks good here. It depends upon what you're doing with the equation. I like slope-intercept because I can picture what the line looks like, but then this would work well if you're trying to put in an ordered pair and evaluate it. So both of those would be okay. All right, I'm going to stop this and get it posted.